Hi everybody, my name is Edgar Martinez. On behalf of Engineering Tomorrow, I would like to welcome you to today's presentation on bridges. I'm excited to have been invited to share my passion and love of structures, especially about bridges today. A little bit about my background. I graduated from the Fu Foundation School of Engineering at Columbia University with a civil engineering bachelor's. I chose construction management as my concentration because I was intrigued about planning, construction, and delivery of multi-million-dollar infrastructure projects. Today's short presentation on bridges will answer questions like, what are bridges? How important are bridges to our everyday life and our society as a whole? And finally, what are the fundamentals of bridge design? At the end, you will be able to use some of your engineering metal to design and create your very own bridge. The challenge will be that your bridge carry the load extremely well while also being economically feasible. Or for clarity, a strong, cost-effective bridge. Take some time to think about bridges. Have you ever wondered what your day would be like if there were no bridges? Do you know the number of bridges you cross every day? Have you ever wondered why the bridges have different designs? Take some time and maybe think, share with a partner some of the ideas. Engineering Tomorrow's curriculum is developed by professional engineers and the engineering interns you see here. We'd like to thank Joanna Cotto, Kira Mallison, and Carolyn Gillespie for their work in creating this breakout. So let's get started. A bridge is a structure that is built to span physical obstacles such as a river or a canyon for the purpose of providing safe passage over the obstacle. There are many different bridge designs, and the choice of which to build varies depending on the function of the bridge, the nature of the terrain where the bridge is constructed, the material being used, and the funds available to build it. Take a look at the bridges that you see on the screen. Notice that they all have similarities and differences. All of these bridges traverse an obstacle, but they all look different, right? The first one you see here is an arc type bridge. Second one is just basically a beam bridge, right? Cantilever, beam bridge. And then the third one, which looks really intricate, is what we call a cable stayed bridge. We will talk more about those bridges as we go along. Just a quick question, maybe you're thinking or wondering right now, how many bridges do you think there are in the United States? 50, 500, 500,000, a million. How many do you think? If you guess somewhere in the 600,000 range, you would be correct, right? This is positive for those of you that are planning to be civil or mechanical engineers because there will always be a job for you. All of these bridges in the United States have a lifespan, which means that they have to be inspected, they have to be maintained, or they have to be rebuilt. As I mentioned to you at the beginning, right, a bridge is much more than a structure. For centuries, communities have been building bridges to make connections that increase opportunity. Rural isolation is still a root cause of poverty today. In some communities, people are cut off from year-round access to education, healthcare, and markets due to the inability to safely traverse some of these rivers or canyons. So how important are these bridges really? Well, they're so important that in some studies of communities, right, those with access to bridges earn 30% higher incomes as a result of the increased access to jobs, education, and medicine. One engineer dedicated to solving the problem of rural isolation is Avery Bang. Avery knew she wanted to be an engineer when she was a kid playing with Legos. She went on to study civil engineering and began volunteering building bridges in rural communities when she was in college. She is now the president and CEO of that organization, Bridges to Prosperity. If you take a look at this slide, even though bridges have different looks and purposes, they all do the same thing. They traverse obstacles. Bridges restore and improve urban infrastructure in several ways. Firstly, bridges are important components of integrated transportation systems, making individual vehicle travel, mass transit, bicycling, and walking all as easy and as efficient as possible, and providing reliable, safe access to many social institutions. If you look at the first picture here, you can see that there's an integrated transportation system. You see some cars, you see some trains, right? I live in New York City, right? So the one that I think about is Brooklyn Bridge, right? The Brooklyn Bridge is iconic. If you ever have a chance to visit New York City, you should definitely walk over it because you're able to walk over it. But it is integrated, right? Because people can walk over it. You have cars going over them. You also have trains going through them, right? So something to think about. Secondly, new materials and construction methods allow for new bridge designs that offer solutions for difficult problems. including bridges over challenging spans of water like you see here, the floating bridge in Washington, right? Or even specialized bridges that can be rolled out in disaster zones, right? So if you look at the bottom left-hand corner, you see that there's a mobile origami bridge, right? These bridges are really intricate, but they can be taken. These bridges are transportable. You can take them different places, you can roll them out, and you can provide safe passage for people who've been stranded, right? Middle of a disaster zone. Finally, building bridges contributes to the joy of living, regarded almost as much as works of art as they aid in transportation. Care in their design can contribute to a more enjoyable urban environment. Bridges will change the landscape of a city skyline. Here in New York, we just recently had the Kosciuszko Bridge put in, and it totally changes what Brooklyn looks like. So think about that as you're designing your bridge, right? You may wish that your design is really pleasing to the eye. Moving on, let's talk a little bit about the fundamentals of bridges. Even though they're all different, it's the interplay between compressive forces and tensile forces. In order to build bridges that will be able to carry the required loads without collapsing, it is important to understand something about stress, strain, and the strength of materials. Stress is a measurement of force over an area. Compression occurs when something is being squeezed together, while tension occurs when something is being pulled apart. Bridge designers must model the stresses that exist throughout the structure under the most severe conditions, including the heaviest loads and the wildest weather conditions. Strain is a measurement of how an object reacts to stress. In order to create the safe designs, engineers use their understanding of forces, stress, strain, and material properties, including the amount of stress a material can take without permanently deforming or breaking. Let's go here. There are many bridge designs. Some of them are more popular than others. Virtually all of them work by balancing compressive forces in some places with tensile forces elsewhere. Architects and engineers from the mechanical, civil, structural, and material engineering disciplines work together to choose the design and materials based on a number of constraints, including bridge function and budget. I do want to show you something about this. If you notice on this slide, you see a whole bunch of different bridges and you see different colors. I'd like you to notice that the blue are where the tensile forces exist in some of these bridges, and the red is where the compressive forces exist. I do want to show you something that I usually use with my students to show about bridges, right? So you can see here an actual bridge. This is a sample of a suspension bridge, right? What you'll notice is that there are two abutments here, and each one of these members carries some kind of load. What I'm going to do is I'm going to run a test on it to see how it would do during loading, right? So I'll start here and I'll pause it first. So I'll pause it there. And what you see before the truck actually passes is that some of these members already have taken different colors, right? So again, the blue means tension, the red means compression. The reason why that happens is because the bridge is made up of material, so it already has a dead load to it, right? It has to support its own weight. Notice that these colors will get darker as the truck passes right over it, right? So as you can see there, right? You can see all of the stresses on each of those members and how they concentrate as you get an actual load going across it. That load is called a live load. Engineers work with all different types of load, right? Dead loads, what's required to keep the building up by itself, and live loads, which includes the crossing of any objects, as well as any environmental factors, right? Think about seismic loads with earthquakes. Think about resonant loads with winds, right? Wind shear will cause a bridge to move, right? So all of those things have to be designed for. So this is a simple truss bridge, right? Warren truss to be exact. Again, each one of these are different members and they're going to be loaded, right? So take some time to maybe predict what kind of loads you expect on some of these members, right? Which one of these, just based on if you were to load it in the middle, do you expect to be compressed or squeezed together, right? Think about which one of those members will be pulled apart. All right, maybe you've had a chance to take some time to think about it. Let's test it again, just so you can see again, there's the bridge, and you can immediately see that you can see some of its deformity already from its own dead load. So you can see that some of these members get kind of pinkish red, right? So those are the pieces that are being compressed, and the blue are being pulled apart or being tense. So let's get a truck over it now, put a live load on it. And here, as you see it crossing, you'll see that those stresses will change, right? So you can actually, some of them get darker, some of them get lighter, right? So something that you might encounter on your testing. Now, the other thing that you will notice here is that each one of these members on the right, okay, notice that they're made by different materials. We're going to talk about material, but we're also going to talk about the shape of the material, which are really, really important in understanding how a bridge carries its load, right? So when we get later on in this presentation, I'm going to show you 3 equations, and you're going to understand that each of these are really important, right? We're talking about the cross section, the size, the shape of the bar, and also the length, right? We'll talk about the length because length is very important. And just think about what would happen if one of these members were really, really long, right? Let's say you didn't have a short member, you had a really long. Do you expect that to be stiff, or do you expect that to be flimsy, right? So something to think about as you go around designing your bridge. I do want to change, just for fun, and I've never really done this. Let's see if we could change one of these members. So I'm going to change this member you see here. I can probably change its material. Let's say right now this is a solid carbon steel bar, right? If I want to change it, right? I want to make it bigger, or I can make it smaller. So you can see here, and obviously I'm doing something I'm exaggerating a change here because I want you to notice the difference, right? So now let's test it. And as we test it, you're going to see immediately that that one fails, right? Right? Because again, we chose a member that was too tiny. Now, why would you want to choose a very flimsy member? Because you want to save some money, right? As I said at the beginning, right? Bridges cost something, right? So if there's no money in the budget, you may try to take shortcuts, right? And sometimes they work, but as an engineer, you have to know which shortcuts you can and you cannot take, right? This would be unacceptable, right? This bridge is not functioning. Let's see if we can, that's my second iteration. Let's go back to the drawing board and let's change that member again. Notice that it has now some hatches over it, just means it's not good. So let's make it a little thicker. Let's say 80 by 80. Notice that it's still significantly smaller than the members around it. Okay, but let's test that. Let's see if it will pass the test here. Again, you see, again, it does not work, right? So back to the drawing board. Let's pick something closer to its original size. Let's do like 140. I want to make it, let's test it again. Here we go. Now you can see that that member is being stressed, right? Hopefully it will take this live load, and it actually does, right? So, it does not. It does not. It does not. So in this case, this would be a bad thing, right? This would not be a good thing. So again, trying different ones because I'm trying to use a word here. Let's do one more. Drawing board. Let's make this 120, 120. I'm just going up incrementally. Again, dead load. You can see that that member is being stressed. Here comes the live load. Will it pass? Maybe, maybe not. In this case, it actually does pass, right? Now, if you were in that truck, you would probably not be happy because that bridge is really moving. And this is a case where that bridge is serviceable, which means that it actually does what it's supposed to do. But people are not going to want to go on that bridge. They don't feel safe, right? So that's something that you really need to think about, right? Even though your bridge is serviceable, it functions. Sometimes you want to make sure that it's strong enough so that people feel comfortable on it, right? If you've ever been on a bridge and stood right in the middle of it, if you're able to walk over it, you will feel the vibrations in the bridge, right? And all structures have to move. If structures don't move, they break, right? Think of something very brittle. It doesn't have a lot of flex in it, right? So as you try to bend it, it'll just snap, right? That's something that you don't want. Bridges, right? We were talking about how important materials are to bridges, right? So here's a timeline of how bridge design has evolved. First, in prehistoric times, right? They were simple, right? Simple bridges. They were made out of natural materials such as fallen trees, right? And it allowed people to cross small rivers and to follow food sources. Then by about 100, 200 AD, bridges evolved to be made with cement and concrete. Roman art bridges were the first style of permanent bridges. They had an iconic structure as shown in this picture. Next came stone bridges in the 600s. One of the oldest surviving bridges built with stone was the Zhaozhou Bridge in China, as shown in this photo. Can you think about why stone is not a good material for bridges? If you thought that it was too heavy, you are right? So stone is heavy by nature, right? So it will not allow you to span large spaces, right? So this is nice for small bridges, but what if you needed to cross something larger, right? Stone would not be good. Why? Think about when we spoke about dead loads and live loads, right? Stone will have a heavy dead load, right? So the longer that you try to make this bridge, the harder it's going to be for it to stand on its own. Moving on. We had the advent of iron. Iron allowed us to build these open spaces, these truss bridges, right? These truss bridges are amazing in carrying load. They do it well, they do it efficiently because of the shape. Think about the shapes that you see in there. A lot of maybe triangles, right? A lot of members there. And they allow efficient carrying of load. But iron does have its problems, right? It can get rusty, right? So even over water, that requires a lot of maintenance. So how do we handle that? What do we come up with, right? We think of another material, possibly. What material? Well, steel, right? Steel was lighter, steel was stronger. And so it allowed us to make these really, really large, long bridges that we can use. A lot of them, think of like the San Francisco Golden Gate Bridge, right? That has a lot of steel in it. All of these bridges made with steel are able to span longer canyons, rivers, obstacles. And so they became the material for bridges. So what will you create next? Let's think about that. All right. So a quick recap of everything that we have spoken about today. We have spoken that bridge designs depends on function, location, material, and budget. Bridges work by balancing compressive and tensile forces. And bridges are designed and built using the engineering design process. Today's bridge challenge will ask you to design, build, and test a bridge to maximize load and do it cost effectively. And you'll get to practice the engineering design process to improve your design. So some of you may be asking, well, what is this engineering design process? Well, the engineering design process is an iterative process where you do something and you do it over and over again, right? So you start by learning, creating a design, building that design, testing it, making changes that you see based on your testing, and then deploying it and doing it over and over again, right? Iterations, you do it over and over again, almost like what I was doing with the bridge designer, right? It took me iterations, right? Changed it a couple of times. So what we want you to do today is we want you to imagine you're a team of civil engineers, and we want your group to use the engineering process to create a bridge that is able to withstand the greatest amount of stress, weight, right? So we're gonna take 2 minutes for you to practice a little bit. I want you to take out a piece of paper, 12 inches or more in length, approximately 3 inches wide, and I'd like you to make a simple bridge, right? Your constraints are very simple. Maybe 2 pieces of paper, no more, 2 small pieces of tape, maybe some pennies so you can load up on it. In my example, I've loaded up an iPhone, but that's not what we want, right? Throw some pennies in there. Make sure that you're testing your bridge by putting 2 books underneath it that are 11 inches apart. Think about what shape you want your piece of paper to be. Is it ideal for it to be flat? Do you want it to have some other shape? Should I roll it, right? Think about different things that you can do to that piece of paper to fortify it, make it stronger, right? Change its shape. Because as you remember, if we go back, right, shape is important for each of these members. All right, hopefully you've had a chance to play with the paper bridge. I do want to go over some bridge design equations, right? So the first equation that we speak about when you are working on your bridge is Hooke's law. Most bridges and structures can be represented with this simple equation. When an applied force F is placed on the bridge, it will respond. It will move, it will displace, it will experience strain proportional to its combined stiffness. The stiffness and the strength are a function of its shape, its material, and how the structure is supported. So looking at this first equation, what I'd like you to notice, right, is that the force is directly proportional to the stiffness and the deflection. So for those of you that don't may not know what that means because maybe we haven't gotten through algebra 2, right? What that means is if I increase the force, one of these has to change, right? One of them has to go up and one of them has to go down in order for it to be constant, right? We can't change the stiffness. K will always be constant, right? Because you're using one material, right? So that doesn't change. So if I increase the force, that means that the deflection, the response is going to increase proportionally, right? So the bigger the force, the bigger the deflection. Hope that makes sense. Now, how can we quantify it? How do we come up with this K number, right? This K constant? Well, K, right, is the bending stiffness, right? And it comes from this equation right here, which you see K equals 48 EI divided by L cubed. If you're not a math fanatic, but you still like engineering, that's okay. You don't need to know exactly what everything means. You just need to know how these variables play with one another, right? So if you notice the bending stiffness, the K, right, is directly proportional to the material and the inertia, the shape, right? So again, if this goes up, one of these has to go up, right? And of course, if these change, it'll change K. What I do want you to notice is that the length is in the denominator. And think about a fraction. If you have a large number in the denominator, what happens to the number? Does it get bigger or smaller, right? So think about that, right? So think about what's the difference between 1 over 1 and 1 over 100. And notice that if you have a big denominator, you have a really tiny number, right? So length also plays a role in this, right? Lastly, if I put it together and we solve for X, I want you to notice, so all I did was take this K, this huge equation that says plug it right in there. I think what everyone needs to notice, right, is that in this last equation, notice that the deflection, right, the deflection is going to be directly proportional to the length cubed, right? That means that you don't want long members because what happens if you increase the length, right? When you increase the length, there's a cube factor, and then that's going to change the deflection. That's why you want short members, right? And you don't need to know this equation, right? Think about the piece of paper that you used before, right? If you had it long, it's flimsy, right? But if you shorten it, it has a little bit more stiffness in it, right? So something to think about. Bridge design practice. What should you have learned from the paper challenge? Shape matters. We talked about it in the equations, right? There are different ways that you could have done your bridge. Here are some U channels, some I channels, L, some T channels. You have some trusses. We talk about ribs and gussets that reinforce some connections, right? You could have added some ribs, right, to stiffen your bridge. So there's different ways of stiffening your bridge. As you start to build your bridge from our engineering kit, I want you to think about all of these things because they do come into play, all right? So a little bit of lab overview. What are you doing? Now comes the fun part, the challenge, right? You're gonna identify the problem. What is your problem today? Your problem is that you will be building a cost-effective bridge that can carry a lot of load. Do some research. What design could you use? Should I use a truss? Does it make sense for me to use a suspension bridge? Do I have material for that? Maybe try a cable stayed bridge. Is it easy to just go simple and make a cantilever bridge? What do you think, right? Think about what materials you will use, right? Design your solution. Draw it out, right? The first thing that you learn in engineering school, at least in construction management, is that all of the cheap choices are made when you're drawing out your diagram. It's very challenging for you to change something once you've built it. So draw it out. Think about all the different choices that you have as you're drawing it out, right? Then build your first prototype. Create your first prototype of your bridge. Test it, right? Fill out the chart in your student workbook to collect and organize your data, and then analyze your results, right? Use your observations and data from step 5 to answer the questions in your student workbook. So a couple of design constraints. These are some things that you have to stick to, like every engineering project, right? When you have a real engineering project, you get a big book. It's all of the specifications for your project, right? Same thing here. You have some constraints. Your bridge must be 12 inches or more in length. It must be 3 inches or less in width. It can be as tall as you need, right? And you can use materials found in your home or in your ET toolkit to build a bridge. Popsicle sticks, wood dowels, tape, whatever's included in there. Testing restrictions. You'll need 2 chairs or 2 tables to test your bridge. Set the chairs or tables 11 inches apart. Place your bridge model on the chairs and tables. Each of the bridge should extend at least 1 inch beyond the chairs or table, right? So Almost if you're putting your bridge out, right? If you're putting your bridge out, you want to have a little bit of overhang, right? That's really, really important. You don't want the bridge to sit right at the end because then you're not really testing it. Remember, it'll deflect or it'll shorten. Test the strength of your bridge using a shopping bag. Add small items until it breaks and calculate the weight of all the items in the bag. Use the iterative process to build a stronger structure. What we have here is a video of someone testing your prototype. So what you'll see here, see an example is there is what kind of bridge is that? Hopefully you said truss, right? It's a truss bridge with a road deck. Glancing at it, it looks like it meets the criteria, 12 inches long, 3-inch wide, right? So that looks about right. And what you have here is he is using a cable tie and a piece of metal to create a testing apparatus. Now, where does it make sense to test this bridge? Right at the middle, right? That's where you want to test your bridge. Because that's where you want the most load, right? And think about why. Why not test it anywhere else? You want to load it in the middle of the bridge because that is probably going to be where you have the most unbraced length, right? And here he goes. He's loading it, right? He's using cans to load it. So he has a shopping bag attached to it. And again, as you load your bridge, you want to start to see how it behaves, right? Your bridge is going to start doing a couple of things. Like all structures, it's going to start to change shape, deflect, right? But it also starts to make sound. All structures make sound, right? So sometimes they're worrisome, right? So think about the sounds that you're hearing, right? Because you hear some cracking, some creaking, right? Think about why that's happening, right? And then really pay attention to how the bridge will fail. Now, I know for some of you, you spent a really long time making this bridge and you don't want to break it, but that's the fun part of it. You have to break it, right? So continue to do it until it breaks, right? And then figure out why it broke there. Was it a connection issue? Was it a member issue, right? And think about ways of making it stronger, fortifying it, okay? Let's move on here. Again, as I mentioned to you, in order for you to analyze your results, right? You want to be able to calculate the cost of your bridge. Here is a small table with some materials and the cost associated with each of those materials, right? Again, let's say you and one of your schoolmates, one of your colleagues, right, made the same bridge. Who made it cheaper, right? In real life, that's what's going to happen, right? If you have a project and you put in a bid for it, most of the time they will choose the cheaper bid, right? So in this case, you want to be as cheap as possible, right? And at the end of the activity, you'll be able to compare your bridges to see which group's prototype held the most weight for the lowest cost. All right. So that is the challenge for today. Okay. Let us review a little bit, right? We spoke about bridges and why they're important to society, right? We understand now that bridges help people who are in rural areas, right? By giving them access to education and jobs and medicine. We spoke about how important bridges are when being designed and how important understanding compressive and tensile forces are important. You have many, many options, different types of bridges that you can make. Do your research and see which one is your favorite. We spoke a little bit about the engineering process, right? How it's an iterative process that you do over and over again. And that's basically what you're going to be doing here. Okay. And then you have your challenge, right? You're making a bridge, you're going to load it, and you're trying to make it as cheap as possible. I wish you well. May your bridges be strong and the cost be cheap, right? And if you wish to continue to explore, if you like today's breakout, you may be interested in topics like bridge design, tunnel design, construction materials, lattice work in buildings, and the type of engineers relevant to today's bridge lab are civil engineers, environmental engineers, architectural engineering, materials engineers, and mechanical engineering. From all of us at Engineering Tomorrow, we thank you for your attention today. And I thank you for allowing me to be invited into your classroom and be part of this process. So thank you so very much.